In this video, our topic of discussion is laws of refraction based on the wave theory. So for this, we are again going to use the Huygens construction principle. So where we are considering two incident rays which are parallel to each other, that is, they are traveling from infinity. They are incident on a surface xy which is a plane refracting surface. So the surface xy is a plane refracting surface. Again, if you observe, the first ray is hitting the surface at point A. Let's say this time is t is equal to 0. Now, if you draw an incident wavefront which is perpendicular to both the incident rays, we can observe that the incident wavefront is meeting the second ray at point A dash, means the second ray is traveling an extra distance A dash B. So let us say in this case the ray is traveling from a medium of refractive index mu1 to mu2, where mu1 is the refractive index of a rarer medium and mu2 is for a denser medium. Okay. So the distance A dash B traveled by the second ray in time t is going to be the speed of the light in this medium. Let's call the speed of the light as v1 multiplied with time, because we know that the distance is speed into time. So once you get v1t, this is after t is equal to 0. This is the extra time that is taken. But at t is equal to 0, the first ray has already hit the surface. So what it will do is it will start producing the wavefronts. It will start producing the spherical wavefronts. Now our interest of study is to find out what will be the radius of the wavefront that is generated by the source at point A in the second medium. So as we know that when the ray is traveling from rarer to denser, the speed of the light is going to decrease. What we need to do is, once you take the compass, measure this distance v1t, so that is A dash b, take a distance slightly lesser than this, because we know that in the second medium it is going to travel a distance lesser. So once you take a distance lesser than this, cut an arc. So once you cut an arc, this is going to be the spherical wavefront that is generated by the source at point A after time t. So from the second point of incidence, if you draw the tangent to this spherical wavefront, that is the secondary, it is a secondary wavelet. So to the secondary wavelet, if you draw the tangent from the second point of incidence, then this will give us the refracted wavefront. Again the same logic, tangent drawn the secondary wavelet is going to give you the wavefront. Here the secondary wavefront is going to be the refracted wavefront which is generated from the second point. So from point A, draw a ray through the point of contact of the refracted wavefront, that will give us A B dash. So this A B dash is going to give us the refracted ray, because the ray and the wavefront are perpendicular to each other, right? So once we do all these things, our work is to prove Snell's law. We know that the laws of refraction are like this. The ratio of the sine of the angle of incidence to the sine of angle of refraction is equal to the refractive index, the ratio of the refractive indices in both the media. So for that, what we are going to do is, if you draw a normal at this point, then this is going to be the angle of incidence. If this is angle of incidence, this is going to be 90 minus I, because the ray and the wavefront are perpendicular to each other. If this is 90 minus I, this will be I, because normal and the median and the boundary are perpendicular to each other. This is I. Similarly, if you draw a normal in the second medium, this is going to be angle R. Then this will be 90 minus R. This is already 90, so this angle will be R. Right? So if you consider the right angle triangles A dash B, then we can see that sine I is given by A dash B divided by AB. But A dash B is nothing but V1 into T, where V1 is the speed of the light in that medium, divided by AB. Whatever AB is, let's not worry about it. Let's take it as equation number 1. Similarly, if you consider the triangle A B dash B in the second medium, then sine of the angle of refraction is given by A B dash divided by AB. This AB dash is going to be a distance of V2 into T, where V2 is the distance of the V2 is the speed of the light in the second medium. So A dash B divided by AB is nothing but V2T divided by AB. Let's take this as equation number 2. So if you divide the first and the second equation, sin I by sin R, that will give us V1T divided by V2T. But so T and T will get cancelled, V1 divided by V2. But we know that V1 and V2, that is the speed of the light, is inversely proportional to the refractive indices, which will be equal to mu2 by mu1. So if you conclude, sin I by sin R will be equal to mu2 divided by mu1, and this is the proof for Snell's law using the wave theory of light.